Chain rule for functions of several variables. Now, the textbook does teach this with an exceedingly large matrix process, which is a proof for the actual chain rule. So it's kind of like the long way. When you learn definition of a derivative, that's what we want to think about the book's instruction for this. I'm going to give you guys a slightly easier way to function with this. So the chain rule for functions of several variables, we're going to talk about that, and then we're going to talk about partial derivatives with implicit differentiation, which is going to cover two different topics in the actual assignments for this week. So first, let's take a look at the chain rule. So the actual definition of the chain rule is basically that I have this dependent variable w, and then I have two independent variables x and y. The easiest way to think of this is like when we did parametric. So we've got x is g of t, so that x depends on the value at t of g, and then I have y, which depends on h of t, but both of those combined are related to w. So think of this a little bit like parametric. It's really important that g and h are both differentiable functions of t, and if that's true, then w is a differentiable function of t, which means that the derivative of w in reference to the derivative of the variable t is equal to the derivative of w dx times dx dt. So think of that like an implicit, oh, I took the derivative of an x, I need to do dx dt, plus derivative of w, reference to y, dy dt, think about the implicit functioning. So if we look at the actual diagram at the bottom, it puts it together in a nice visual way for you to be able to see what's happening here as we're differentiating x first with respect to w, then y, and then we're doing that like implicit follow-up or chain rule follow-up. Think about it as if you have a chain like u squared, it's 2u du dt, or 2u du dx, or something like that. So it's a little bit of implicit feel, a little bit of a chain rule feel. So here's the first example. So we have w. W is defined as x squared y minus y squared. Then I have the extra piece where, hey, x is sine t, y is e raised to the t. Find dw dt. Well, in order to find dw dt, I'm going to have to do some things with this x and y because x isn't just x. X is really sine of t. And so the question becomes, well, why didn't they write sine squared t? Well, because then it would not be as fun. So there's not a really great answer for that. But as we get higher and higher in multiple variables, it becomes a lot easier than if I was writing out trig functions and logarithmic functions and things like that. So it actually does do a little bit of not helping you feel visually overwhelmed. So if I'm doing the chain rule, I'm going to have to take the derivative of the first and the second term, which is going to be the first term. When I take the derivative, remember this from partial derivatives, when I'm doing the derivative of x, it treats y like it's a constant, which is where 2xy comes from. And then I have dx dt. So I'm just going to take the derivative of x squared y like y was a constant. So I would do the derivative of x is 2x, and if I have a constant like, say, 4x squared, it's really 4 times 2 times x. So that's where the y is coming from, right here in front. Then I have to do dx dt. So that's when I go here and I say, okay, well, what's the derivative of this? Well, the derivative of sine is cosine, and so that's where this piece comes from. Then I'm going to say plus, which I know it's a minus sign, but we like to keep things positive. So I have y squared. So if I do y squared, that would be the derivative of y, and then I'm going to do that times dy dt. So if I go back and I differentiate this in terms of y, that means that x squared is a constant. So the derivative of 2x is 2, right? So that means the derivative of x squared y, x squared is just a constant, so it's actually going to be x squared. Then I'm going to have the derivative of minus 2y squared, which is going to be minus 2, because you bring the 2 to the front, you have 2y. Then you have to multiply that by dy dt. So dy dt, the derivative of e to the t is e to the t. And so once I go from there, that's my long statement. Now I'm going to have to do some algebra to simplify it. So the key here is remembering, got to differentiate it with x, where I'm treating y like a constant. Then I have to differentiate it with y, like I'm treating x like a constant. And we're going to add those together always. So then I can basically distribute things through and replace x and y with their values from the problem. So that's what this line is I took x is sine t, y is e to the t, and I replace things in here. So instead of 2x, it's 2 times sine t, and instead of y, it's 2 times sine t times e to the t. So that's where this line is coming from. And then here, I just take it and I distribute that e of t through the back, and so that I have this situation. Now they want me to find it at t equals 0. So if I plug in t equals 0, something really nice is going to happen here. The sign of 0 is 0. So that means this entire term and this entire term are gone. And so I'm left with negative 2 e to the 0. Well, e to the 0 is 1, so I'm actually left with negative 2. So that's a walkthrough. You do not have to do the matrix process in the homework example. You can follow this process, and this should really help you get through that section quite a bit easier. The proof is great, but we also want to make sure we can deal with it. So the chain rule for this theorem can be extended for any number of variables. So if I'm doing any number of variables, I would take the derivative of x with y held constant, take the derivative of y with x held constant, or if I have 3 variables, say I take the derivative of x where y and z are both constant. Take the derivative of y where x and z are both constant. And then last, you would take the derivative of z where y and x are constant, and you would add those 3 together. So that's how you do the chain rule, avoiding that giant matrix, is by holding 2 things, or holding all but one thing constant and cycling through the derivatives. So here we have a chain rule if I have 2 independent variables like we just walked through. Like I said, we're going to go ahead and hold one constant, so we can hold y constant and then differentiate x, hold x constant, differentiate y, and then we make sure we're multiplying by those dy dt's. And so we can continue branching this out among more variables the more we see this actually happening. The exercise keeps things fairly simple. So here, another example, we're going to try one with 2 independent variables. So we're going to use the chain rule to find dw ds and dw dt for y equals 2xy. So here, x is s squared plus t squared, 2 variables there. Y is s over t, so 2 variables there. Using this theorem, I can hold t constant and then differentiate with respect to s. Okay, so then if I did that, if I hold t constant and I differentiate with respect to s, I'm going to do dw dx, and then I'm going to have to multiply that by dx ds. So there, I'm going to have to make sure that I'm treating s squared as a variable and t squared as the constant. So that's what's happening there. So I'm treating, in the first statement, from here, dw dx means I'm taking the derivative of x where y is constant. So the derivative of 2xy would be like the derivative of 4x. The derivative of 4x is just the number in front, 4. So if y and 2 are constants, the derivative of that is 2y times dx ds. So because it's dx ds, I'm treating s as the variable and t as a constant. So that means that it's 2s, and the derivative of t squared is actually going to be 0. Plus, then I'm going to differentiate where I'm going to hold y as the constant. So then the derivative of 2xy, y is the variable, x is the constant, is just 2x. And the derivative of s over t, where I'm holding s as the variable and 1 over t as the constant, because I'm doing dy ds, so I'm differentiating with respect to s, it would be like having 1 over t times s. The derivative of 1 over t times s is 1 over t. So that's where this comes from, okay? I know it's complex. You might need to rewind and watch that again, but it's all about treating something as constant. So once I have that huge statement, I'm going to substitute my values in. So now it's a little bit uglier to look like. And then I'm going to algebraically simplify. So s times s is s squared. 2 times 2 is 4. And then I still have the t at the bottom. Here I'm going to have 2s squared plus t squared, which would be 2s squared plus 2t squared, because I'm going to distribute the 2 through. And I can do 1 over t is the same as dividing by t. If I do that, they have a common denominator, so I can combine the 4s squared and the 2s squared into 6s squared. The 2t squared's hanging out, and so that is the end of that portion of it. Now, if I hold s as a constant so that I can complete the second half of the question, then that is going to give me a different derivative statement. So if I'm holding s as the constant, that's going to give me a different look as I do those derivatives again here. So it doesn't affect the 2y. It does affect this piece, because now if s squared is constant, the derivative is 2t. And if s is constant, the derivative is the derivative of 1 over t. So when I do that, that is going to yield a different result, because the derivative of 1 over t is negative 1 over t squared, and s is a constant, so it still hangs out. So that's where this line is coming from, is I'm treating s like it's the constant, so the derivative of t squared is 2t, and then the derivative of 1 over t is negative 1 over t squared times s. So I had to do it twice. I had to treat t like a constant, and I had to treat s like a constant. Then I'm going to do the same thing, combine and get like terms. Whoops, sorry. Do the same thing with distributing all my variables through, simplifying just like I did the last time, and this is what I get for that statement. So I get 2 solutions here because of what I did. Now, this can then extend and keep going forever. So if you have 2 independent variables that are defined in those subset equations, it can get a little tricky, but it's definitely a doable process. Now let's look at some implicit differentiation. I think this one clicks a little better than chain rule personally. So an application of the chain rule is when we do a derivative implicitly. So in that situation, we're going to say x and y are related by a given equation. So f of xy is 0, say. We're going to assume y equals f of x is differentiable. It's always an important assumption. Then we're going to find dy dx using the chain rule. So let's consider that I've got a function that's defined of an x and a y here. Then I can use theorem 13.6 to say, well, I'm going to differentiate with respect to x, and then I'm going to have the derivative of x with respect to x. Then I'm going to do the derivative of y with respect to x. What does that actually look like? So once I simplify that procedure down, so I've got my procedures here, and I'm setting equal to 0 because I know that f of xy equals 0 for all x's in the domain. So if I'm looking at implicit differentiation with the chain rule, they're coupled together in this situation because, like I said earlier, it's almost like when you're differentiating x, you put dx, then what it's in reference to, so dx dt. It's the same idea as implicit differentiation. So that if I'm looking at the derivative of z in reference to the derivative of x, that means that I'm finding f of x where I'm holding one thing constant, and then I'm holding my z so that I'm holding one thing constant. So it's identical to what we just did. So what does it look like in practice? I know those theorems are great, they're wonderful, but it's really hard to visualize them. So if I'm finding dy dx, given this is an implicit, right? This feels like an implicit from Calculus 1. I'm going to start by defining the function f as f of xy equals this function. So that's just a little notation change. Then I'm going to use the theorem 13.8 to say, okay, if I do it this way and I maintain that y is going to be a constant, the derivative of all the constants is 0. So 0, 0, 0. The derivative of x squared is 2x, which is where the negative 2x comes from. And then if I treat the x as a constant, then I would have 3y squared, 2y, negative 5. So that would give me 3y squared plus 2y minus 5. Once I have those statements, I will take the negative f of x divided by f of y. So I'm taking this, the derivative of x, when I'm holding y constant, divided by the derivative of y when I'm holding x constant. So it's kind of a funky way of doing like parametric, when you're trying to find dy dx in parametric. You're going to differentiate the x, you're going to differentiate the y, you're going to divide them. Same idea here for implicit. So for implicit functions of variables, this is how we do it. And so then you simplify, and there's your answer. So implicit derivatives are probably a fair amount easier than chain rule derivatives, but still a little bit sticky. I hope that helps. You also have examples in the actual course section. There's a PowerPoint and a lecture video there you can follow up with for additional help, and always, of course, your textbook.